Okay, welcome to Let's Get to the Marks. We're looking at carboxylic acids. I'm on Physics and Maths Tutor. This is a brilliant website. Yeah, it does have a lot of adverts, but it's an incredible website. You can find tuition on here, but more importantly, it has a totally free bank of questions and answers for all exam boards, for all the science A levels and maths. So here I'm going to carboxylic acid and derivatives, and we're looking at AQA. And if we come here to these are the recent papers, you can click on that. And let's get into it. Carboxylic acids and derivatives. Which statement about CH3 2 CHCH2 COOH is correct? And we've got four possible answers here, so let's get into it. The first thing I'm going to do is draw the structure of this molecule out. So what we can see here is we've got two methyl groups and then a CH. So let's get those down first. So drawing this first methyl group. So what I'm going to do is I'm going to go through all of these in detail. Obviously, you can do these much quicker, but this is just to give you the extra explanation that's not given to you on the mark schemes, okay? So I'm using the structural formula here to draw out the displayed formula of this molecule. So I'm onto that CH group there that I've circled. Now we've got a CH2, and then we got the carboxylic acid functional group, which is coming off here with an O and an OH. Carbonyl group and the hydroxide group. So in aqueous solution, does it react with magnesium to form carbon dioxide? Well, this is a weak acid, remember? So acid and metal from GCSE, you know, doesn't release carbon dioxide, releases hydrogen. So this is simply a metal in an acid. So let's look at B because A is definitely not the right answer. So let's have a little look at B. It can form hydrogen bonds. Well, in order to form hydrogen bonds, you're going to need one of three different types of bonds, an OH bond, NH bond, or FH bond. Does this have an OH bond? Of course, we've got the alcohol group there on the carboxylic acid functional group. So B is going to be the correct answer, but let me go through the other two now. So C, an optical isomer, this is going to need a carbon with four different groups attached, you know, a chiral carbon. And if we check these, okay, this methyl no, none of these have got four groups attached. This one, four different groups anyway, and the last one only has three groups, so it's definitely not that. IUPAC name, is this 2-methyl butanoic acid? Let's check it out. Okay, well, you can see here the main chain has four carbons in, but actually we don't number it that way. We're going to number with the carboxylic acid functional group as carbon number 1. So this is actually going to be 3-methyl butanoic acid. So this is not the correct name. 2-methyl butanoic acid is not the correct name. This is 3-methyl butanoic acid. So the answer to question 1 is B, and that was a pretty roundabout way to get to that. But hopefully you appreciate the detail and the explanation. Okay, question 2. Which compound is formed when phenylbenzene carboxylate is hydrolyzed under acidic conditions? So we got four answers here, A, B, C, and D. Let's go ahead and draw out phenylbenzene carboxylate so we can work out what the product of its hydrolyzation is. So what the hell is phenylbenzene carboxylate? Well, remember, a phenyl group is simply a benzene ring that's a side chain of another molecule. And then we've actually got a benzene ring here as well with the name benzene. So that means we've got two benzene rings in this molecule. And then we've got carboxylate, and that's like ethanoate, propanoate, the part of an ester that comes from the carboxylic acid. Or if you have a salt of an acid, something like sodium ethanoate, then that's the carboxylate group. So here we go. We've kind of got combine all of these together. So I've got myself a benzene ring. And by the way, I'm going to be doing this in three parts. There's 14 questions in this first carboxylic acids and their derivatives. So I'm going to be doing this in like three parts because there's no way I'm going to be able to do all 14 in one video. So here's the molecule. It's basically got a benzene ring, then the carboxylate group's in the middle there, and then we've got another benzene ring. Okay, neat. Okie dokie, where are we? Right, so we've got this carboxylate group, we've got this benzene, we've got the phenyl. And what you can see is that if you hydrolyze this ester link here in the middle, what's going to happen is you're going to use hydrogen or water to break that down as it's hydrolyzing. So during hydrolysis, we're going to add an OH to the carboxylic acid group, and we're going to add an H to the O there to make an alcohol. So really, when you break up an ester type bond, you're going to form an alcohol and a carboxylic acid. So that means our product A, B, C, or D that it's talking about has to either be an alcohol or an acid. So when we look at this, we can see that A is plausible because A is a benzene group and it has an OH group. It's an alcohol. Okay. The reason I'm crossing it out is because of that carbon. It's not in the right place. And then we look here, and this is an aldehyde. CHO is the functional group. So that's an aldehyde. So that wouldn't get formed under hydrolysis. And then we've got, what is this molecule? Well, this looks like a ketone. Do you notice it's got the carbonyl functional group, the CO, in between the methyl group and the benzene ring? So this looks like some sort of ketone. So again, this wouldn't be formed. So we're really looking for an alcohol or carboxylic acid, which is what you get when you hydrolyze that ester link. And here you go. We've got our carboxylic acid. Recognize that from this drawing up here. And so that means that D is the correct answer. Well done if you got that right. All right, hit the like, subscribe. Let's go. Okay, this is question 3. This question is about esters, including biodiesel. An ester is formed by the reaction of an acid anhydride with, it looks like ethanoic acid here. We'll be given the structural formula. Complete the equation in your answer to show clearly the structure of the ester. Give the IUPAC name of the ester. So we really need to complete this equation, show the two products for 2 marks, and name the ester that's formed. So you've got an acid anhydride here. That's this thing with the double carboxylic acid group. And essentially, if that was a hydrogen atom attached there like that, which I've drawn in black, instead of another carboxylic acid, then you would just form an ester and a water molecule in a condensation reaction. But instead, what we've got going on here is the carboxylic acid, the oxygen on there, is going to join there, and we're going to remove that carboxylic acid. So you really just want to form an ester between one of the carboxylic acids of the acid anhydride and this alcohol. So just make an ester from that carboxylic acid, which is propanoic acid, and the alcohol, and you'll be left with another carboxylic acid. All right, let's show how this works. So yeah, instead of water being released, we've got a carboxylic acid being released. So let's draw this out. We've got CH3, CH2. We're drawing this top carboxylic acid from the acid anhydride. But instead of writing the oxygen here, we're going to attach the oxygen from the alcohol. And this alcohol is ethanol here. So let's attach this. I'll do this in a different color, just so you can see where it's coming from. I've circled the alcohol in green. We're going to attach the alcohol now. Now remember, during this reaction, the hydrogen atom's removed from the OH group. So there we go. We have our ester. So that's going to get us 1 mark for this structure. Now, when naming esters, remember you're going to name the name of the alcohol that formed the ester forms the first part of the ester's name. So this was ethanol, so this is going to be ethyl. And then the second part of the ester's name comes from the carboxylic acid. And so there's 3 carbons in that. So it's going to be propanoic acid and ethanol. What do you make? Ethanol propanoate. And you should know this from GCSE, especially if you did triple. So we've got ethyl propanoate, and we've given the structure. So what is there left to do for the 3rd mark? Well, the 3rd mark here is for working out what the other product is, where I've put my green arrow here. This other product circled in black, this is the other half of the acid anhydride. And of course, I've drawn a little black H on there, and that's exactly what's going to happen. A hydrogen atom is going to join, and we're going to have propanoic acid breaking off as well, which I'm writing here in blue. So we've got the structure for both of our products. They especially wanted the ethyl ethanoate, the ester. We've got our carboxylic acid, and we've named the ester ethyl propanoate. So that's all 3 marks. Well done if you got that right. Remember to pause the video before having a go at these. Okay, part B to this question, let me just make it a bit bigger. This is the dreaded biodiesel. So in a reaction to form biodiesel, 1 mole of vegetable oil reacts with an excess of methanol to form 2 moles of an ester with a molecular formula of C19H34O2 and 1 mole of an ester with a molecular formula of C19H36O2. Draw the structure of the vegetable oil, clearly showing the ester links. You should represent the hydrocarbon chains in the form of CXHY, where X and Y are the actual numbers of carbon and hydrogen atoms. So you should know this reaction off by heart. It's a pretty laborious one to learn and loads of people don't. But essentially, vegetable oil plus 3-methanol or excess methanol is going to give us a glycerol molecule and some methyl esters, normally 3-methyl esters. And they've given us the 3-methyl esters here. We've got one which has the molecular formula C19H36O2 and one which had two which have the formula C19H34O2. Now, those are the molecular formula. Don't get that confused. That's not telling you the nature of the fatty acid chain. That's telling you three separate esters that have formed. So we're going to draw those out over here. So what it doesn't tell you in the question is that these are methyl esters. So they start with a methyl group. That's the H3C group I've written here. Then we've got the ester link followed by the hydrocarbon chain. Okay, so why have I got 2 times methyl group ester link then C17H31? Because we were told there were 2 with H34 and O2. Now the methyl group reduces those hydrogens. So as you can see there, these two together equal 36, the H3 and the 33 from the hydrogen carbon chain. So we've worked out our 3 esters. Why did we do that? That wasn't what the question was asking. Well, we're just starting at this basis. So you also get a glycerol molecule, and you don't really need to work this out. This is this molecule I've just drawn here. 1, 2, 3, propantriol. We don't really need that. That's glycerol. But that would be formed in this reaction. And we don't need this either. This is the 3-methanol molecules, metanols, no, 3-methanol molecules that are going to react with our vegetable oil. Now, here's where we get to the vegetable oil. This is the thing that we're actually being asked to work out in the question. So now we've worked out what our esters look like. I'm circling this bit. These bits are going to be identical over in our vegetable oil. So we're going to have 2 of the first chain and 1 of the second. Okay, so what I'm doing here is drawing out the vegetable oil. So why have I put C17H31? Because that's what was on my ester. And all you're doing is swapping those methyl groups on the front of those esters, those C3H or CH3 groups, for the start of the vegetable oil over here. And you just got to learn the structure of the vegetable oil. The only thing that differs with the different vegetable oils is the size of the carbon hydrogen section, where we've written C17H31. So that's the only thing that's actually going to differ here. The rest of it is always going to be the same. So you can learn the structure of the vegetable oil. You should know the structure of the methyl esters and the glycerol. So this is for the formation of biofuels from vegetable oil. And there we go. This one is slightly longer because this is from the ester, the longer ester with the C19H36O2. So great. Okay, yeah, there's our ester link. We've clearly shown that, which was part of the question. So there you go. That's 2 marks for our vegetable oil, 1 mark for the ester links, 1 mark for the correct carbon hydrogen numbers on those 3 chains. Okay, let's move on. So for part C, it says the compound C19H34O2 is the methyl ester of ZZ or ZZ octadeca 912 dianoic acid. What a serious name that is. Part of the acid structure is shown. Complete the skeletal formula to show the next part of the hydrocarbon chain up to carbon number 14. In your answer, show the Z stereochemistry around both the C double bonds. Now that sounds very intimidating. But the main thing we've got to think about here is we've got some double bonds, and where are they? Well, they're going to be on carbon 9 and 12, and they've handily numbered 7 and 8 for us. And they want us to just do 9, 10, 11, 12, and 14 in a skeletal formula. So we haven't got to draw anything fancy coming off of this. So we're essentially just doing 9, 10, 11, 12, 13, and 14. Now, you wouldn't actually, when you write the skeletal formula, write all these numbers out, but this is just to show you. Now, unfortunately, the structure I've just drawn here is not correct because there's no rotation around the double bond. What we want to do is show that. So we give it a slightly different look. We're going to go like this, and this is going to show that there's no rotation around the double bond, and this is how the cis trans arrives. And this is ZZ, so this is Zusammen or sisters. So they're both going to be on the same side. So let's delete the numbers and we're left with this lovely structure. And if you're wondering how this is cis or ZZ, it's got the hydrogens all would be coming off on this side, okay? And they'd be stuck there because there's no rotation around the double bond. So there you go. That structure there is the correct answer. Okay, give an equation for the complete combustion of the ester C19H34O2. So we just write C19H34O2 plus oxygen forms carbon dioxide and water. Really easy. You just put the 19 from the C there in front there and 34. We need 17 of them to double up on the water. And then we need to work out the oxygen, which you always do last with your combustions. So 9 times 2, we've got 38 oxygens from the carbon dioxide. We've got 17 from the water. 17 and 38 is 55 oxygens left over that we need on the left-hand side. So we come back to the left-hand side and we go, ooh, what's 55 divided by 2? Is it 22.5? No, my brain is rubbish. It's 27. Hold on. 27.5 is 55 divided by 2. So we go, oh, 27.5. But then actually that's incorrect as well, because 27.5 times 2, we forgot about these two that we already have. So actually we only need 53 oxygens to balance the left-hand side. So we do 53 times 2, and that's 26.5. And so 26.5 in front of this O2 plus the 2 in our C19H34O2 makes 55, which we've got on the right hand side. And you can have any multiples of this. So if you don't like dealing in half, some people don't, you can double all of this. Okay, part E. Combustion produces greenhouse gases such as carbon dioxide that cause global warming. Part of the infrared spectrum of carbon dioxide is shown in the diagram. State how the infrared spectrum of carbon dioxide in the diagram above is not what we would expect from the data provided in Table A of the data booklet. Well, if you look in Table A of the data booklet, we would expect carbon dioxide to be around 1,680 to 1,750. That's where the COO bond from the carbon dioxide should be. What we actually find here is we've got an absorption at 2,300 and 2,350, sort of around that range is where the absorption is. We would expect it not to be there. On the data book, it should be 1,680, but there we go. Okay, and then the next part of this question is, so we would expect blah, 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 blah. Yeah, moving on. Explain how carbon dioxide causes global warming. So loads of answers you can give here, but essentially the bond absorbs the energy at the 200, 2000, whatever we quoted there. Yeah, 2300 to 2350. That's the wavelength of the energy. I've written just energy, but that's stupid of me. That's the wavelength of the energy that it absorbs, the CO bond in the carbon dioxide, which means that less energy is released to the atmosphere or emitted. You can say more energy is trapped or heat energy is trapped in the atmosphere. Cool. Let's get down to the final question for this this video on carboxylic acids. I'm going to do the rest of these questions in my next video. Which compound is formed by acid hydrolysis? Phenyl methyl ethanoate. Well, if we break down that word phenyl, we've already talked about the phenyl means it's a benzene ring that's a side chain. We've then got a methyl group attached and the ethanoate. So this is like, yeah, whatever. Uh, there we go. There's the structure. So remember that this has come from a carboxylic acid and an alcohol, so likely to be ethanoic acid and then the alcohol with the benzene ring. So which compound would be formed when we split that? So go through A, B, C, D, see if you can work it out. Here's what phenyl methyl ethanoate would look like. And now go through, separate it into a carboxylic acid. You can do that with the carbonyl group, separate it into the alcohol. The O in the ester link always comes from the alcohol. So I'm circling around the benzene ring, the CHH and the O here, which come from the alcohol. And this second circle I'm making is the carboxylic acid. So now work out which one of these products could have possibly come from either half of that phenyl. So if we look first at A, we can see we've got a benzene group C6H5, that stands for benzene. Then we've got CH2, then OH. So that looks pretty good. If we draw that out here, we've got the benzene. Coming off of it, we've got CH2, which is just what my diagram has above. And then we've got OH. So that's the correct answer. But let me go through the others for you. You've got one here. This is an aldehyde. So benzene ring with a CHO on it. Now we've got a ketone, we've got a benzene ring with a carbonyl group in between the methyl group and the benzene ring. So that's not going to form when you break up a phenyl methyl ethanoate or a phenyl ester or whatever we want to call it. And then we've got a carboxylic acid down here. Now, technically, the carboxylic acid could have been made, but you can see from the diagram up above, the carboxylic acid is not attached directly to the ring, and this one would be attached directly to the ring. So this is not the correct answer. D is not correct because it's not directly attached to the ring. So there we go. Question 5. Acyl chlorides are useful reagents in synthesis. They react with aromatic compounds and also with alcohols. CH3CH2COCl reacts with benzene in the presence of AlCl3 in an electrophilic substitution reaction. Give an equation for the reaction of CH3CH2COCl with AlCl3 to form the electrophile. Outline a mechanism for the reaction of this electrophile with benzene. So you really got to give the equation, and a mechanism is worth 4 marks. So just the structural equation or the chemical symbol equation and the mechanism. Okay, so we're looking at an acyl chloride functional group up there. So we've got ethanoyl, no, it's propanoyl chloride, it looks like. Um, so here you go, propanoyl chloride. You've got the COO and the Cl. We're going to add that to AlCl3, and this is going to create our electrophile. This is known as a halogen carrier, AlCl3. Okay, and it's going to form AlCl4. It's going to steal the chlorine off of the acyl chloride, leaving a carbocation, leaving a positive carbon atom, which is going to be a really strong electrophile. Now, you can put the positive sign over the O or the C on that structural formula, but if you write the displayed formula, it has to go onto the C. Okay, so it's always best just to position your positive over the C there. Now, the AlCl4 minus has picked up the chlorine, and the AlCl3 is a halogen carrier. It helps us make a strong electrophile by stealing a halogen. Okay, and it's kind of a catalyst because it reforms after the equation, but we don't need that here. Okay, so let's do the mechanism. That's going to get us our first mark. We've got 3 marks left, which we get from the mechanism. So let's have a look at this mechanism. So what I'm doing is I'm circling the electrophile here, very strong electrophile. It's been made by the halogen carrier. So what type of mechanism is this? If we're involving an electrophile, it's obviously going to be electrophilic, and this one happens to be substitution. So here is our electrophile. Notice I've put the positive sign on the carbon. Don't put it over the oxygen. And this is our kind of ethanoate or propanoate ion right now. So our carboxylate ion or propanoate ion. Now, I've drawn 2 versions of it. So one's with all the display bonds and one with the structural down below. Now, that's a big fat cross because we need the arrow coming out of the ring in the benzene because only electrons can move. Protons, positive charge doesn't move. It's trapped in the nucleus. So the ring is a high electron dense region or an electron rich area. So it does attract these electrophiles, and then the electrons jump out the ring and form a bond with the positive carbon atom here on our electrophile. So we're now going to draw our intermediate, and our intermediate is going to have a hydrogen atom. Just remember, just show you here, benzene has a hydrogen atom coming off of every one of the 6 points. So it's got C6H6 is its formula, but we don't like to show those hydrogen atoms unless we're showing them involved in a mechanism. So we can rub all of those out and just leave the one that we want to, the point that we want to attack. So we're going to leave one hydrogen atom here. You just have to imagine the other 5 are there. And of course, I need to put my delocalized ring in the middle. What I'm doing now is adding some dots. This is because once our delocalized ring is broken, we mustn't extend it beyond the two carbons either side of the carbon we're attacking. So I mustn't extend this past sort of C2 or C6 and C2. Okay. And now what I've got, that's the horseshoe. You won't get the mark if you draw those lines too close together. So now I've attached the electrophile, but we have four bonds here around that carbon atom. Now, carbon is in group four, has four outer shell electrons, loves four bonds. Why can't it do four bonds with a benzene ring when it's attached to a benzene ring? And that's because one of the electrons from each of the six carbons has to be donated to the ring. So, in order to reform the benzene ring so the whole thing doesn't fall apart, it must donate, well, it must receive electrons to reform the ring. And that comes from the bond between the hydrogen atom and the ring there. So the hydrogen and the carbon in the ring. So those electrons will be sent back into the ring. We've got to draw an arrow from the bond going to the broken ring. My notes, I've got a cold at the moment, so I apologize for all the sniffing you can hear in the background. So literally, that's it done, completely done. That's your three marks there. One for the arrow in the first step, go into the positive there. You got one for the broken ring with a positive sign in, and one for the arrow there, and then we have one for the equation. So it's all. Okay, so that's all the marks, the mechanism and the equation. What I'm going to do now is go ahead and show you something that you don't need. You don't need any of this, but it's what would it look like afterwards and how do we regenerate the halogen carrier? So this is useful just for your knowledge, for your revision. You might get a question on it. Well, here we go. Here's our final structure. So what the hell's that? Yep, it's a ketone of some sort because we've got the carbonyl group in between. We've also got our AlCl4 minus is going to join with that hydrogen over here. I'll just circle this hydrogen here. This hydrogen up there, which I'm circling in pink, is going to join with the AlCl4 minus that we created in the reaction to make the strong electrophile, and it's going to recycle our halogen carrier. That's why it's a catalyst. Okay, nice. Let's go on. Let's get into the organic product in B. So, part B, the organic product in part A can be converted into the alcohol shown. So, we've got a new thing here that's made from what we made in part B, part A, sorry. Give the name of the alcohol, IUPAC, give the reagent needed for this reaction and the name of the mechanism. Now, I'm going to get a bit extreme here. It's only 3 marks, but I'm going to show you how we get from A to B. So, the molecule we made in A is this lovely molecule. And if you're wondering what it's called, we've got a benzene side ring attached to a carbonyl group. So it's phenyl propan 1-one, as we've got 3 carbons in the chain. And of course, the important one is the one with the carbonyl group on it, and that is attached to the phenyl. Okay, now we need to look at why this gets attacked. Well, the carbon is delta positive and the oxygen is delta negative. So that's going to make it like the likelihood that it's going to get attacked by nucleophiles right here. And our nucleophile is a hydride ion that's come from this reducing agent, which is NaBH4. You could also use LiAlH4 as well. Yeah, and that's got a stupid name like sodium tetraborohydrate, some nonsense like that I can never remember. The less frequently used but also acceptable strong reducing agent is lithium aluminium hydride. Much easier to say. That's the LiAlH4, and that can provide us that hydride ion, that nucleophile, to attack that positive carbon on the carbon atom. Yeah. Okay, so next what happens? We've got our lone pair, which is negative on the oxygen because the double bond was broken. So that makes it very attractive now for a positive ion, like a hydrogen ion. Where do we get a hydrogen ion from, you say? Well, we can get it from H3O plus, which is essentially hydrogen ions free in water, or we can get the hydrogen ion if we add an acid. If we acidify it, then we have a source of hydrogen H plus ions as well. And of course, although this is slightly complicated because of the benzene ring, this is essentially a reduction reaction where we are reducing an aldehyde or ketone, in this case a ketone, into an alcohol. So you've done this loads of times. Ketones form secondary alcohols, so this will be a secondary alcohol when reduced. And if it was an aldehyde, it would form a primary alcohol when reduced. But the mechanism is actually nucleophilic addition because of the nucleophile at the start, the hydride ion, and addition because we have two products and we end up, two reactants and we end up with one product. Now, why is it not called phenol? Well, because the OH group is not attached to the ring. It's a benzene ring side chain stuck to propanol here. And it's propan 1-ol because the hydroxide, the OH group, is on the first carbon. And it's going to be 1-phenol, propan 1-ol. So the benzene ring, which is a side group, is also attached to the first carbon. So let's score those 3 marks here. We've got the IUPAC name is 1-phenol, propan 1-ol. The reagent we used is NaBH4. Remember, you can use LiAlH4, I'm not even going to say it, lithium aluminium hydride. And of course, the mechanism was nucleophilic addition. Right, awesome. Let's move on to part B. Did I say part B? I think I meant part C. So the alcohol shown in part B, the alcohol we just made, reacts with ethanoyl chloride, that's an acyl chloride, to form an ester. Remember, acyl chlorides react just like carboxylic acids, okay, and end up forming esters. So very similar. The only difference with a carboxylic acid and an acyl chloride is a carboxylic acid has an OH on the functional group and an acyl chloride has a chloride. So here is my alcohol that we just made in the last question, and it's got two lone pairs attached to it, hence the two sets of dots. That makes it very attractive to certain regions, like the delta positive region on an acyl chloride. Acyl chlorides are delta positive, okay? They've got the little positive sign on the carbon. Why is that? Because both the oxygen and the chlorine atom that they have attached are electron withdrawing, so they make that positive. Okay, so they're extra positive compared to carboxylic acids. Now, what happens is that the lone pair from the oxygen attacks that positive carbon, and then don't forget that that double bond between the carbon and the oxygen. So the first two key arrows in this mechanism I've circled here in blue very badly. Now, we're going to draw the structure of the ester that's formed. So as I'm going a bit extra, I'm doing the mechanism, not that we need it, but just to show you what happens. So now what happens is the double bond's been broken. So the oxygen on the acyl chloride has a lone pair and a negative sign. This means the chlorine atom needs to bugger off because there's not room for all of these things to be attached. Okay, and the oxygen atom that was on our alcohol has now got a positive sign, a plus sign on the O. When you write a plus sign on the O is whenever you see 3 bonds around an oxygen. Now we add the arrows in to show the lone pair from the oxygen going back to reform the double bond, to reform the carbonyl group, the COO, and the chlorine atom is snapping off. So what we're going to get is a final product here where we have an ester formed, okay? And we've got kind of a propyl group with a phenol attached there to the carbon that's attached to the oxygen. My oxygen has still got a little positive sign on it, which we don't want for long. And we also have a double bond to the carbon and a methyl group coming off the side there. What happens to that chlorine that snapped off in the previous step? Well, the pair are attracted to the hydrogen. Remember that oxonium ion can't stay stable like that. So this gives the oxonium ion the chance to chip off the hydrogen, dump the electrons onto the positive oxygen and stabilize itself. And the final product I'm going to draw up here, which is the 3rd mark in this question. This is the structure of the ester. I've gone all around the houses, but essentially to name this ester, you're going to see the carbon atom that's attached to the oxygen. That is carbon number 1 on an ester. And so we've got a phenyl side group attached to that carbon number 1. So it's 1-phenyl. And then we've got propyl and ethanoate. Remember, you named the alcohol bit, the propyl first, and then the bit from the acyl chloride or carboxylic acid last. Now, did you need the name of this? Absolutely not. What you actually needed was the observation. So, what you would see happening, the name of the mechanism, and the structure of the ester. All I've done so far is do a dirty ass mechanism and given you the structure of the ester. Let's do the other things. Well, look at this hydrogen and chlorine. They're going to form hydrogen chloride, and hydrogen chloride, we're going to see misty fumes. So that's what you would observe with this reaction. That's your second mark. You get one for the structure I've drawn top right. So observation, structure, we need the name of the mechanism, and we kick things off with nucleophilic addition, because you see that blue bit there, that's acting as a nucleophile. And then addition, because the first two reagents join together to form our intermediate here in black and green. And then we have elimination, because this hydrogen chloride is being kicked off at the end. I mean, personally, these things should be called nucleophilic substitution, because you add stuff together and then you eliminate something, make substitution, right? But they like to get funky in A2, and so they call this nucleophilic addition, elimination. So here we have make sure you pause the video, by the way, and then have a go on some scrap paper that you can chuck away after. So we've got some sort of reactant. In step one, it's split into two different things, an alcohol and ethanoic acid. Then we've got a halogenoalkane at the end of step two, and then an unknown compound S, and then we have some sort of amine at the end of step four. So give the reagent and conditions needed for step one, show how you'd state how you'd obtain a sample of the alcohol formed from the reaction mixture. So first thing to note is, what is the reactant in step one? Can you spot anything interesting about this reactant? Well, it's got an ester link. You should be able to recognize that functional group. This is an ester. And so what happens to esters when we break them down into two products? Well, we get an alcohol formed. This looks like butan-2-ol, this alcohol, and we get ethanoic acid. So, well, we don't necessarily get ethanoic acid, we get carboxylic acid. This is a derivative of ethanoic acid over here. We'll talk about its name later on, because I think they ask you its name later on in the question. So what's happened? How do you turn an ester into an alcohol and carboxylic acid? You hydrolyze it. That means you break the bonds and you split it, and it goes back to the two of the reactants the ester itself was formed from. And so we have an alcohol and a carboxylic acid. So it says, state how you'd obtain a sample of the alcohol from the reaction mixture. First of all, give the reagent. Well, look, there's a sodium ion added to the carboxylic acid in the ester. So we'd need sodium hydroxide. This is actually called base hydrolysis, because we're using a base. Now, what condition do you use for base hydrolysis? Well, you use reflux. Okay, so that's the method you need to know. Once again, I recommend revision cards. They're absolutely awesome for revising organic chemistry, and the best way to do it. So you'd be like, the question you'd have on the front of the card, you maybe had 3 or 4 questions, but would be something along the lines of, name the reagent and conditions for base hydrolysis of an ester. And so you'd be sodium hydroxide, reflux. We'd normally use dilute sodium hydroxide, but it's not on the mark scheme that it has to be dilute. Okay, and then it says here, how would you separate the alcohol? Well, the alcohol is going to be we've got a salt on the right. We don't need to worry about that, but the alcohol needs to be separated from any excess ester. And so you're going to use distillation, or if they've got similar boiling points, you use fractional distillation. And how do you know if something's got a similar boiling point? If it has a similar MR, it's going to have similar strength van der Waals forces, so the boiling points will be similar. Okay, those are your 3 marks. Let's move on and stop all the waffle. Draw the structure of compound S. For each of steps 3 and 4, give a reagent and one condition other than heat. And this is the last part to this question. So let's go to compound S and have a little look. So in order to find out what compound S is, you kind of really need to talk yourself through all of the steps to work out what's going on. And sometimes look past compound S at the final step, because this will also help you. So we're trying to figure out, first of all, what is compound S? Well, it's been formed from a halogenoalkane. So this is the content you need to know in your CGP or your revision guide or your notes, is what can be formed from a halogenoalkane. or a haloalkane, as they're sometimes known? Well, if you do nucleophilic substitution of an alcohol, you can see we've got butan-2-ol. You can make 2-bromobutane here. But they're not really asking us about step 2. But this just helps us. Now we look at compound T. What's happened to compound T? Look, there's 4 carbons in the alcohol and 4 carbons in the haloalkane. By the time we get to compound T, we've got 5 carbons. So in step 3, we must be adding a carbon. And the only way to do that is by using a nitrile group. So again, nucleophilic substitution here. We're going to swap that nitrile group for that bromine atom. Okay. And what is going to be a source of nitrile ions? So you should be thinking about that as a reagent for step 3. What's a source of nitrile ions? And what's the formula of compound S going to be? Well, just swap out that bromine for CN. So CH3, CH, CN, CH2, CH3. And that will get you a mark. That's going to be the structure of compound S, because you're going to be swapping the CN where the bromine is. And of course, you've added an extra carbon. So what was the source of the nitrile ions? Hopefully you came up with it. We can use potassium cyanide or sodium cyanide, okay, KCN or NaCN. And you want to dissolve these in ethanol. And the reason why is ethanol is a really good solvent for polar and non-polar substances. So we will have scored our first 2 marks. Now we need to know what's the reagent for 4. So what do you need to go from compound S, which to what? How do we get from our nitrile over to our amine over here? So, well, let's think about the bonding. You've got a carbon atom joined to a nitrogen with 3 covalent bonds. We need to wipe out 2 of them, it looks like, and add 2 hydrogens to the N to make the amine, and add 2 hydrogens to the 5th carbon on compound T. So what are you actually adding? Well, you're adding hydrogen, H2. You've got 2 molecules of H2 added here. And you're going to need a platinum or nickel or a palladium catalyst. There's a bunch of other catalysts you can know. I just remember platinum and nickel for this one. So once again, I recommend you writing up a revision card and asking yourself, what is the reagent for this particular reaction, and writing the answers on the back. It's the only way to learn organic chemistry is through revision, memorization. Best to use revision cards. Here are the 3 answers you needed to get the last 3 marks of this 8-mark first question. So that is the structure of compound S. You need KCN and ethanol, and that is for the reagent and condition for step 3. And then the reagent is hydrogen to make the amine, and you need a platinum catalyst. You could say palladium or nickel. There you go. That's the reagent and the condition. Super. Let's move on to the next question. Question 7. Coconut oil contains a triester with 3 identical R groups. The triester reacts with potassium hydroxide. So you can see we've got 3 KOH reacting with a triester in coconut oil. Complete the equation by drawing the structure of the other products of the reaction in the box. Name the type of compound shown by the formula RCOOK. Give 1 use of this type of compound, and that will get us another 3 marks. So first of all, I just want to show you that our 3RCOOK has come off. So we need to remove that from our reactants on the left. Whatever's left over, we just combine to make the product in the box. So we're missing CH2, CH2, and 3 OHs. And of course, this is going to be a molecule of glycerol, or propan 1,2,3 triol, which is the IUPAC name. So you can, this is like a displayed formula I'm showing here, but we can also write out the structural formula, which is probably better for this question. And the next part of the question, we've got name the type of compound shown by the formula RCOOK. So you have to really look at what that is. That is some sort of carboxylate ion, and it's got a potassium. So potassium carboxylate, or we could just call it a potassium salt. Okay, and you get these when you break up an ester with base hydrolysis. And you can see what happens is a positive potassium ion from your source of potassium, like KOH, joins on to the lone pair on the oxygen on the carboxylic acid group, on the carboxylate ion. So you get potassium carboxylate or a carboxylate salt or a potassium salt, and the use of these is soap. Okay, so nice easy 3 marks. Let's move on to part B, which is an amount of substance question. So the triester in coconut oil has a relative molecular mass of 638. In the equation shown at the start of this question, R represents an alkyl group that can be written as CH3CH2N. Deduce the value of N in CH3CH2N. Show your working. So we've been told that the MR is 638. And what we need to zing back up here, check this out, right? We need to find out what R is, right? They're asking us what is R. So the first thing we need to do is subtract all of this from 638. All of the COO and the CH2, CH2. We need to add that all up using our periodic table and our relative atomic masses to create the MR of all the stuff that we need to remove to be left with the 3 R's. Once you're left with the 3 R's, divide by 3 and you've got the MR of R. And then you can work out by a bit further subtraction what the MR of R is. Okay, what the MR of the CH2 section is, and then you can work out what N is. So let's have a little go. First of all, I want to take my 638 and I need to get rid of the kind of the glycerol component here, the CH2, CH2. I need to get rid of that. So let's add that up. So that's 18. And it's not really glycerol because it doesn't have hydroxide ions attached, but it's 18, 13, and 14. So that's a total of 41. I'm going to need to take that off of the 638. And then I've got 3 times COO. Do you remember we had each of these connected to this structure, which I've given 41 to? Well, a carbon atom has 12, and oxygen, 2 oxygens are 16 each, 32. So that's 44. And we got 3 of them. So if I add 41 to 3 times 44, I get 173. So I want to rip that all away from the 638. Now, I'm not done yet. Look at what it's asked us to deduce the value of. It's asked us to deduce the value of N. So we just want the CH2 in the brackets. We don't want those CH3s on the side. And each of the R groups starts with a CH3. So what I need to do now is add up CH3, which is 12, plus 3 is 15. And I need to subtract, I've never heard of that word. I need to subtract 3 times 15 as well from the 638 because I need to remove 3 CH3s to just leave me with 3 CH2Ns. So when we do 638 minus 173 minus the 45 for the 3 CH groups, we're going to end up with 420. But remember, the 420 represents 3 R groups or 3 lots of CH2N. I need to just find out what 1 lot of CH2N is. So I'm going to do 420 divided by 3. And that is going to give me 140. So I'm going to get 140 equals 1 lot of CH2N. Now I need to work out what N is. Let's add up how many CH2s go into 140. Well, CH2, carbon's 12, hydrogen's 2, because one hydrogen atom is 1 AR, so total of 14. So divide 140 by 14 and we'll get 10. So N is 10. There are 10 CH2s in each R group. So N is 10. Hope that helps. Make sure you hit the like, you subscribe on all of that. It really helps my channel. And if you leave a comment, YouTube even checks the algorithm and it will get my videos out to more A-level chemistry students. Nice one. Well, let's finish up. We've got another part to go, part C, and it's another amount of substance question. So 1.450 grams sample of coconut oil. So a 1.450 gram sample of coconut oil is heated with 0.421 grams of potassium hydroxide in aqueous ethanol until all the triester is hydrolyzed. So we're going to hydrolyze all of the triester in the coconut oil. The mixture is then cooled. The remaining KOH, some of the KOH is left, obviously, that must be excess, is then neutralized and by exactly 15.65 centimeter of 0.1 mole per decimeter of hydrochloric acid, just flick down to show it's the 6 marker, calculate the percentage by mass of the triester in the coconut oil. So this is really like a back titration because they've hydrolyzed all of the ester with 0.421 grams of KOH, but we've got some of that mass of KOH must be left over. And so what they do in a back titration is they take that leftover KOH and they neutralize that fully with an acid, normally where it has a 1-to-1 reaction, which it does in this case. So they've used 15.65 centimeter cubed of 0.1 mole per decimeter of hydrochloric acid, and that has neutralized the KOH. So from that, we can work out the moles of hydrochloric acid. As it's a 1-to-1 ratio with the KOH, we can work out the moles of the KOH. We can subtract that from the original moles of the KOH, which we can work out also, to find out how many moles of KOH reacted with the triester. We can then use the ratio of triester to the original KOH and work out the moles of triester used, the mass of triester, and then the percentage mass in the coconut oil. So you should pause the video right now and have a go with a pen on a scrap bit of paper using all the data and the numbers you've got. Okay, there's several points you could start here. You could start by working out the original moles of KOH from the 0.21 grams. But I'm going to start right at the bottom numbers we've got, which is with the hydrochloric acid. Now, we know that hydrochloric acid reacts in a 1-to-1 ratio with KOH. Now, how do I know it's 1-to-1? Well, I could write the full equation out and balance it. But if you look at potassium hydroxide, there's one hydroxide ion in KOH, and there's one hydrogen ion in hydrochloric acid. So they're going to come together perfectly to make one molecule of H2O. So I know it's a 1-to-1 between the acid and the alkali or the base in this situation. So anyway, let's work out the moles of HCl. And in fact, we're working out the moles of KOH that were left over. So we're going to use N over CV, which you should know from your triangle. And we're going to do 15.65 divided by 1,000 times 0.1. And that's going to get us, if we whack that in the calculator, 0.001565 moles of HCl. We know it was 1-to-1 with the KOH, so which tells us that we got 0.001565 also moles of KOH. And that was the moles of KOH left after it reacted with the triester. So now what I want to do is find out the original moles of KOH that reacted with the triester and minus the ones left over to find out how many moles of KOH actually were used up in the reaction with the triester. So the original moles of KOH at the start was 0.421 divided by 56. That's because the relative atomic mass of potassium is 39, oxygen 16, and hydrogen's 1. So it has an MR of 56. Remember, mass over MR equals moles. We'll find out that we started off with 0.0075 moles of KOH. After the reaction with triester, there were 0.001565 left. So I'm going to do 0.0075 take away 0.001565, and I found out how much KOH was used up with the triester in the hydrolysis. And what we're going to get there is 0.005935 moles of KOH reacted with the triester. Now, if it was a 1-to-1 reaction with the triester, we'd also have 0.005935 moles of triester that was used up, but it's not a 1-to-1 reaction. Can you remember from earlier on in the question how many molecules of KOH react with one triester? remember it's a 1:3 ratio, as in one triester molecule reacts with 3 KOH. Remember that OH is used to form the glycerol and to break that bond with each of the R groups. So we need to do 0.005935 divided by 3 to find out our moles of triester that we originally had that were completely hydrolyzed. And the answer is 0.0019783 N, or moles of triester. That is how many moles of triester we had. So you've got most of the marks now. We just need to use that M over MR times moles and convert that back to find the mass of triester in that many moles. Remember that the MR was 638 of our triester in the coconut oil. So we need to do MR times moles. So 638 times 0.00197883. And we're going to get a mass of 1.262, whatever that is, 17 grams. And we're going to divide that by the original mass of the coconut oil, because not all of it is triester. So we're going to go 1.26, 217, and divide that by 1.450 grams times 100. And that's your final answer for your percentage by mass of triester in the coconut oil. No, it's always best to keep all, if you're really good with a scientific calculator, the best thing to do is to keep all your numbers in the scientific calculator from the start of your calculation to the end. That way you get closer to the true value that they want in the mark scheme. I got 87.04, so I could just round that to 87%. They accept anywhere from 87 to 87.1%. So there we go. Right, the final part of this question is D. And that is the final part of this walkthrough. I'm going to do another carboxylic acid walkthrough, part 4, pretty soon in the next week. Suggest why aqueous ethanol is a suitable solvent. Okay, so why is ethanol a suitable solvent for this reaction? Well, if you check out triesters, they've got this. We've already found out earlier in the question that there's a CH210 bit, right? CH3, CH210, the R group. And that's going to be fairly non-polar, right? There's no positive and negative elements, delta positive, delta negative there. Yes, we've got the ester bond, which has got some polarized parts. And you've got the alcohol, you've got the, potassium hydroxide, which is obviously a polar molecule as well. So we kind of want a solvent that combine together a non-polar and a polar reactant and mix them together. And what we find is that alcohols have a non-polar bit themselves, i.e. ethanol has the CH3, CH2 bit, which is non-polar, and then it has the OH bit, which is polar. So it's very good at combining and mixing together polar and non-polar reactants. Ethanol makes sure the KOH and the triester can mix. Ethanol makes sure they're miscible. Now, the safety precaution here is use a water bath. Don't use a Bunsen burner flame because ethanol's flammable. That's the justification. Okay, so you gently heat. Let's get to the marks. Big shout out to the members, Nicola Korzik and Ash Ford. Thanks for supporting the channel. Let's get into this one. Question 8. This question is about making a diester from cyclohexanol. State the type of reaction in step 1, give the name of the reagent needed for step 1 and the type of reaction and reagent. We've got 2 lines there for putting it. It's worth 2 marks. You can see we've got an alcohol going to an alkene to compound G, then going to a diol, and then down below we've got like a diester. You can see those ester links here and here. So what is the name for the reagent in step 1? Well, we're going from an alcohol to an alkene. So alcohol to alkene, hopefully you know what that is. The type of reaction, that's a dehydration. You can say elimination. Remember, you're removing a water molecule. You're removing that hydroxide group and a hydrogen as well. And that's going to leave us with that double bond. We call that dehydration or elimination. Okay, and the reagent we need is H2SO4, that's sulfuric acid. And that will score you 2 marks for this first question. Don't forget, you might want to grab some scrap paper, a pen, a calculator, pause the video and have a go at the start of each question. Right, state the reagents needed and give the equations for step 2 and 3. So let's check out step 2 and 3. And it does tell us explicitly, show the structure of compound G in your equations. So we need to show the actual structure of that. So let's look at step 2. We're going from this alkene and we end up at a diol. right? So what we're going to need to do in between is become a haloalkene. We're going to do like electrophilic addition or some sort of addition, nucleophilic, whatever. But we're going to do some addition and we're going to end up with a haloalkene. So step two, my reagent is bromine. You could say chlorine, iodine, or any other sort of halogen. So you know that one from your AS content. Yeah. Now, haloalkanes can also be called halogenoalkanes. It all just depends on what you like. So we're going to add bromine here. It's going to add across the double bond, and we're going to get a dibromo cycloalkane form. Okay, let's look at the next one. So we want to go from that. What happens if you want to replace those with OH groups? That is just straightforward substitution. We can do that using a strong alkali, something like sodium hydroxide or potassium hydroxide. Now we do need to redraw compound G. So we're going to redraw that here. And then we're going to add sodium hydroxide. As I say, you could add lithium hydroxide or potassium hydroxide. And we're going to need two sodium hydroxides because we need to replace those bromines with two hydroxide groups. So that's a bit of substitution. We're probably going to get sodium bromide formed, and you're going to get two molecules of that form. My kids are going nuts next door, so if you hear lots of screaming and stuff, there's no axe murderers in the house. It's just my kids trampolining off the sofa. Right, part C, cyclohexane 1,2-diol reacts with ethane diol dichloride. Give the name of the mechanism for this reaction. Complete the mechanism to show the formation of one ester link in the first step of this reaction. Right. This reaction is going to be nucleophilic addition elimination. You probably can get away with just saying addition. Okay, let's zing down and check out the rest of this question. So we've got the mechanism here. Now, funnily enough, if you go onto the mark scheme, I'll put them in the link. If you go onto the mark scheme, they kind of just messed up on the mark scheme here and they didn't have an answer. So that's what I'm going to show you now, how to go through for this. So they want the first part of the mechanism. I'm going to show you the whole addition elimination mechanism. Might as well, eh? Right, so what's going to happen? We're going to look at one hydroxide first just to form one ester link. So we've got the lone pair being donated from the hydroxide group to the carbon. Why? Because it's delta positive. You don't need to show the delta positive in AQA, but the carbon is slightly positive because that's a polar bond. Now, the oxygen will temporarily break the double bond in order to allow a bond to form with the hydroxide ion. Otherwise, carbon can't have 5 bonds. So I'm going to redraw out what it looks like now. So in order to get the marks for that, you'd need two curly arrows and the lone pair on the hydroxide. Now, what we're going to do over here, we're going to redraw it out. We've got a lone pair and a negative sign on the oxygen. So you now have to include the negative sign on the oxygen. We've got the Cl still attached and the COCl at the bottom there. So what's going to happen here? Well, this is an oxonium ion. This oxygen now has 3 bonds around it. So we put a plus sign on that. And we're going to put the lone pair from the oxygen going back to reform the double bond. The chlorine, therefore, cannot be allowed to stay because that would mean carbon has 5 bonds around it. So the chlorine is snapping off to allow the double bond, the carbonyl bond, to reform. So I'm going to redraw it again. Again, there's 2 curly arrows there, a plus sign on the oxygen and a lone pair with a negative on that oxygen. Now we're going to redraw it. I've still got the plus sign on the oxygen. However, the double bond has reformed. The chlorine has buggered off. And I've still got the COCl at the bottom. Now I'm going to put my lone pair chlorine over here, my anion, because it's snapped off. I've circled it in green. Obviously, the way I've drawn it's a bit awkward because it's like crept over there, but never mind. I've still got this bit because we're not showing that form an ester link. That can also form an ester link with the hydroxide group, but the question didn't want that. So now I'm showing the lone pair from the chloride ion attacking the hydrogen on the oxonium. The hydrogen can only form 1 bond, so it's going to join with the HCl. That's what's the elimination part, and it donates its pair of electrons to the positive charge on the oxygen, cancelling that out. Okay, so the reason why we call this bit elimination is because you're going to get hydrogen chloride eliminated. I mean, sometimes when you're dealing with carboxylic acids and you're not dealing with acyl chloride type molecules, you'll get water eliminated. So it'll still be elimination. But this elimination step, the hydrogen chloride gets eliminated. Right. Suggests why chemists usually aim to design production methods with fewer steps with a higher percentage atom economy. So Basically, if you have fewer steps, you're going to save energy and you'll increase the yield. Remember, each step in a chemical reaction involves the yield getting less because you're going to leave some powder behind. You're going to get some reactants not fully reacting and all of that kind of stuff. And high percentage atom economy means you probably have less products and the more useful products, less wasted products. Okay, check out this method for making aspirin. Add 6 grams of salicylic acid to a weighing boat. Place the weighing boat on a 2 decimal place balance and record the mass. Tip the salicylic acid into a 100 centimeter cube conical flask. Step 4 is missing. We're going to be asked about that. Add 10 centimeter cubed of ethanoic anhydride and to the conical flask and swell. You can pause the video and read through that if you really fancy it. Right, A, describe the instruction that is missing from step 4 of the method. Why is this step necessary? So what should have happened after you weigh something? Can you tip it into a flask? What should you do next? You should re-weigh the weighing boat or the crucible or whatever you've been weighing in. You need to re-weigh it so that you can get an accurate calculation of the amount of mass you've actually added. You might have weighed out 6 grams, but by the time you tip it in, maybe only 5.98 go into the flask. And that's because you'll leave like 0.02 or whatever, 0.002 or whatever will be left behind. You're going to leave a little bit left behind in the weighing boat. So suggest a suitable apparatus for measuring out 10 centimeter cubed of a liquid. So I would use a 10 centimeter cube pipette. Obviously, if it was 2 centimeter, you're not going to get a 2 centimeter cube pipette. But you could use a measuring cylinder. You could use a burette. There's other ways you could do it. I always like the pipette because each pipette only measures a set amount. So you definitely can't make any mistakes with that. Identify a hazard with concentrated phosphoric acid. It's corrosive, so that thing is going to burn up your skin. So yeah, that's the hazard. Right, D, complete the equation for the reaction of salicylic acid with ethanoic anhydride to produce aspirin. It's 1 mark. Basically, what they're getting you to do here is work out the formula for ethanoic anhydride, the structural formula, where you show the brackets and you show how everything's joined together. You can write the displayed formula in order to help you write the structural formula. So ethanoic anhydride. So you're looking at like 2 carboxylic acids, 2 ethanoic acids joined together. With that oxygen linking them in the middle. So what we want to do here, I'm going to draw out the structure of ethanoic anhydride. So we've got a methyl group, we got the carbonyl bond, then we come down to an O. So it's like a carboxylic acid that's had another carboxylic acid added to it in place of the hydrogen atom there. So there we go. With an elimination of water, obviously, you join these 2 carboxylic acids together, and this would be their formula, CH3CO times 2, and then you've got the little O that joins them in the middle. That is on the side on its own, and that will get you that mark. Okay, moving on. E, we have an amount of substance question. 6.01 grams of salicylic acid, Mr138, is reacted with 10.5 centimeter cubed of ethanoic acid anhydride, Mr102. Reaction yield is 84.1. Density is 1.08 gram per centimeter cubed for ethanoic anhydride. Show by calculation which reagent is in excess. So I know straight away I'm going to need mass over Mr times mole. So even if you ain't got a clue where to start, look, straight away I would start here. Like I've been given 6.01 grams and I've been given the Mr. Bang, I can work out the moles of the salicylic acid. Just make sure you label it on the paper so you don't forget as you're scribbling all over the paper with your answers, you don't forget. So the examiner is going to come through and hand you out marks for all these calculations you do. So just make sure you label them so you know what you're talking about. So now, my answer might differ slightly from the mark scheme because I might do some rounding, like this is 0.04355. I probably should just leave that in the calculator, but for speed, I'm round, so my answer might not be 100% correct, but the method is. But you just might need to leave it all in your scientific calculator. So there's my salicylic acid moles. The next thing I want to do is work out ethanoic anhydride moles. Now, they haven't given me the grams of ethanoic anhydride. I'm going to have to work that out from its density. So I've been told I've got 10.5 centimeter cube, that's volume, and if I do volume times density, I'm going to get the grams, I'm going to get the mass, and then I can use the Mr to work out the moles. So have a go at that. So I'm going to do 1.08 for the density times 10.5 for the volume. So density times volume gives me mass, and that should be 11.34 grams. Now that I've got the grams of ethanoic anhydride, what we can do with that, I can divide that by the Mr and that will give me the moles, right? So I'm going to divide it by, oh my days, I can't even write out a number, 102. So I'm going to divide it by 102, which is the MR of ethanoic anhydride, and that's going to give me the moles of ethanoic anhydride. And I've got 0.111111, whatever, 8 moles. Okay, now, do I have to put all of like that? Well, again, you could do some rounding and whatnot. So just check. You should leave it all in your scientific calculator, but I'm breaking it all down because I'm doing it step by step. Okay, that way your answer will be more accurate if you don't keep. Oh my gosh, I can't spell ethanoic acid. Oh no, ethanoic anhydride. That should say ethanoic, by the way. That's just my crusty spelling. I'm not going to go back and change that. So which is in excess? Is it the salicylic acid or the ethanoic anhydride? They're both in a 1-to-1 ratio, so we just need to look which one is bigger. And the answer is the ethanoic acid, 0.111 moles, is bigger than 0.0436 moles, right? So the ethanoic acid is in excess. We can even work out if we want and show the examiner, ooh, I can tell you how many moles would be left over. So 0.0675 moles of ethanoic acid is in excess. It's left over that many moles. If you want, you could work it out with the grams by times it by MR and say how many grams are left over, but we're not going to do that. So ethanoic anhydride is the reagent in excess. Now what I need to do is work out, the next part of this question was to work out the grams of aspirin that are produced. So I'm going to use, they've given us yield. So we need to use the yield calculation. So yield, percentage yield is the actual mass over the maximum mass times 100. So we need to find the actual mass. And so we need to work out the maximum mass and then we can do it. So we know the MR is 180 and I know the moles of aspirin. If everything went perfect, I have to look at the limiting reagent to how much aspirin I could make. I can't look at the excess reagent because that's going to have leftover moles that are unreacted. So I look at the limiting reactant and that is salicylic acid. 0.0436 moles of aspirin is the max I can make because that's the max amount of salicylic acid we have. It's a 1-to-1 reaction. So I'm going to do 0.0436 times 180, and this is going to give me the maximum grams of aspirin I can make, and it's 7.848 grams, not moles. I put N, choose Louise. Right. Bear in mind that I probably could have used 0.04355, which was in my scientific calculator, but I couldn't be bothered to write all those numbers down. So now I'm going to do 84. I'm going to set this out as an equation. Now that should be grams, by the way. Let's just change that so we don't get too confused. 7.848 grams, whatever. I should really round that to 7.85. I'm getting super sloppy today, peeps. Okay. So X is my unknown actual mass. What do I need to do? Well, I've got times 100 there. Divide both sides of the equal sign by 100, and I'll end up with 0.841 times 7.84. And that is going to give me X. So I end up with 6.60 grams. Now, it might be like 6.58 on the mark scheme or whatever, but, you know, the method's all correct here. So, boom, well done. Right, let's move on and finish this pack of carboxylic acids. I'll be glad to get this one out of the way. I started this one about a year ago and just haven't got around to finishing it off. Okay, zing down. F suggests 2 ways in which the melting point of crude aspirin collected in step 9 would differ from the melting point of pure aspirin. Right, crude is a mixture, right? Remember, crude oil is a mixture. Crude means there's other bits inside there. So it's a mixture. How do mixtures differ than pure substances? So they differ with their melting points. The crude substance will probably have a lower melting point, but also it's going to melt over a range. A crude substance or a mixture will melt over a range. So if its melting point was 78, it might start melting at 76 and not stop melting until 82. So it has a range, whereas a pure substance will melt at an exact melting point. Right, crude aspirin can be purified by recrystallization using hot ethanol. Boiling point 78 degrees is the solvent, so ethanol's boiling point is 78. Describe 2 important precautions when heating the mixture of ethanol and crude aspirin. Right, well, think about ethanol. What do you know about it? It's an alcohol. They're flammable. They're used in fuels. I mean, they use ethanol or they use alcohol in cars, in combustion engines in Brazil. So use an electric heater. Don't use a naked Bunsen burner flame. That's what we call flames, and because it might set fire to the ethanol. And also keep the boiling point below 78 degrees. If you keep the boiling point above 78 degrees, then the ethanol, which is a solvent, will evaporate and you'll lose your solvent. So keep the boiling point below the boiling point of ethanol, so below 78, and use an electric heater, not a naked Bunsen burner flame. Right. H. The pure aspirin is filtered under reduced pressure. A small amount of cold ethanol is then poured through the Buchner funnel. Explain the purpose of adding a small amount of cold ethanol. Now, there's 2 points there. The fact that they've said small amount could get you a mark, and the fact that they've said cold ethanol could get you a mark. So, we want to use cold ethanol because it will remove soluble impurities, and we want to use a small amount because we don't want to dissolve any of our aspirin and dissolve any of that and run that off and lose that when we filter. Also, oh, sorry, not insoluble, soluble impurities. Also, we want it to be cold because, again, if it's hot, we're more likely to dissolve some of the aspirin, which we don't want to redissolve any of the aspirin, which will dissolve in the hot solvent. So we cool it so we don't dissolve the aspirin. And yeah, if it's hot, it will increase the amount of stuff that can dissolve in it, which is not what we want. All right. Where are we? Last part to the pack. A sample of crude aspirin is kept to compare with purified aspirin. Describe one difference in appearance. Right. If you have something that's a mixture, you're going to get like, so aspirin is white. Pure aspirin will be white. A mixture will be an off-white color. Why? Because there's more than one thing in it. So if you mix different paints together, you're going to get like a mixed color. But if it's pure, you're just going to get something made of one clear color. It'll be shinier. It'll have larger crystals, more pointy, sharper crystals. Not all different all sizes of crystals. So if it's a mixture, you're going to get a mixture of shapes, sizes, colors. Okay, last question, question 10. Which of these involves addition, elimination? So when we look at this, we can just look at these and quickly work out the mechanisms. So what have I got here? I've got double bond forming. That means I've got elimination or dehydration, but there's no addition going on here. It's just straight up bang elimination. And then for C, I'm looking at C now. C's a double bond I'm seeing with chlorine adding across the double bond. That's a straight up addition. There's no elimination there. And then I'm looking at this final one. I've got the bromine atom. This is a haloalkane or halogenoalkane becoming an alcohol. That's substitution. So we've got like nucleophilic substitution going on down there. So that's definitely not it. So the answer's B. And we've already done this mechanism quite a few times. We've done this type of mechanism quite a few times, but just to show you again, I'm not going to do the whole mechanism, but just to show you again, we've got the addition section of this where the lone pair on the oxygen is going to go to the carbon because it's a polar bond. The carbon's delta positive. The carbon's going to temporarily, the carbonyl bond is going to break. That's the addition section. We've got nothing being eliminated there. And then the next two parts of this reaction involve elimination, and we're going to have the hydrogen chloride molecule eliminated. So first of all, we've got addition and then elimination. Oh my God, I can't even speak properly. So yeah, I'm not going to do the rest of this, but yeah, you get the coup. Yeah, whatever. Right. I should have a chlorine atom coming off there. Never mind. Okay, skip all of that. What I'm going to say, guys, you know what I'm going to say. Yeah, ignore this molecule I've drawn here. Ignore this bit, but you get the idea. Awesome, awesome, awesome. Whiffle, waffle, waffle. Enough of that, Tom. Make sure, guys, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll see you guys in the next video.
You're still here? It's over.